This video is about the Lagrange error bound. The Lagrange error bound is used to calculate the maximum possible error of a Taylor polynomial approximating a function at a certain point. Let's break this down further. Where do we use the Lagrange error bound? It's where a Taylor polynomial is approximating a function. This is what we see here, where we have an original function and a Taylor polynomial has been constructed to approximate that function. And that Taylor polynomial is centered at A. Let's quickly see how a Taylor polynomial is constructed. That's how this polynomial has been built to approximate the original function. It's actually using the derivatives of the original function to do that. We will come back to this form later. And now you get the idea of where the Lagrange error bound is used. So before I tell you what exactly the Lagrange error bound is, let's focus on what error is first. In this context, error is basically how good the Taylor polynomial fits the original function. So we can calculate error at a certain point. This is error at an arbitrary point C. The Lagrange error bound does not necessarily give the exact error. It's a bound, and it's basically like an upper bound. The Lagrange error bound says what the maximum error is when calculated at a certain point for a certain approximation. So, the Lagrange error bound can tell us that whatever this error may be, for example, it can't be more than this. We're trying to find that upper threshold. Now that we have some intuition behind this, let's take a look at the formula that we use to calculate the Lagrange error bound. Although this looks a little overwhelming at first sight, let's break it down part by part. So, C is the point at which the error is being calculated, and A is where the Taylor polynomial is centered, and N is the degree of the Taylor polynomial. So if we look over here, that is basically the highest derivative that you had to take. Now, M is possibly the most frightening part of the Lagrange error bound, and it's a little ambiguous, but don't worry, we'll break it down together. M is the maximum value of the n plus first derivative on the closed interval AC. So remember, A and C have been defined over here, so that's basically what's making up the interval. And the n plus first derivative is best understood with an example. For example, if you had a fifth degree polynomial, then you would be interested in the relative maximum of the sixth derivative of f, the relative maximum being basically the maximum on this interval. Now, sometimes m turns out to be greater than this relative maximum in some cases, but don't worry, you won't have to figure that out yourself in those cases because basically m is going to be given if it's ever like that. So, some other things to be aware of is that M is usually either A or C. Look, it's not as frightening as you might have thought. First, you might have thought, oh my gosh, how do I calculate the maximum value? But it's usually either one of the endpoints on the interval. Basically, when the n plus first derivative of f is decreasing, it's going to be A because that is greater than C. When it's increasing, it's going to be C because C will be greater than A. And usually in the AP problems, you're going to get an n plus first derivative that's either only increasing or only decreasing. A tip here is that if you do get a Lagrange question on the non-calculator section, then you can either use this reasoning over here, or, what they might do is they might give you like a function such as e to the x. And you know that the derivative of e to the x is going to be e to the x no matter how many times you take that derivative. So in that case, you can be quick about it and just say that m is equal to 3. So of course, there are some shortcuts like that. Another tip is that we usually have m equals 1 for anything that involves cosine or sine. 1 is the amplitude for a non-transformed sine or cosine function. See, 1 is the amplitude. And if there is a scale factor, like, if you had 4 sine of x, well, then, of course, you would use 4 as your m because that would be the new amplitude. So now, let's do an AP FRQ. For this example, we will only be looking at part D. Our end goal is to explain why f of 0 is negative. Right, let's keep that in mind. Some prior information that I'm just going to hand over is that f of 0 was estimated to be about -5 in part C. So, our first step is just to write down the formula. N will be 3 and A will be 2. And C is 0. But what is M? Let's look at this information over here, which happens to be on this interval. So M is basically the maximum value over here. We're seeing the derivative is less than or equal to 6. So that tells us that 6 is going to be the maximum value that we need. All right, now let's plug everything we have into the formula. How do we simplify this? So, when you're in an AP exam, when you look at this, you might be confused and feel like you need a calculator. But if something like this comes and you don't have a calculator, what are you going to do? Let's expand 4 factorial. So now we have an important piece of information. The error is less than or equal to 4. But now this is still not our final answer. So we're going to use the Lagrange Error Bound, basically what we just calculated, to do something very interesting. We can use it to construct an interval for what f of c can possibly be. Remember, f of c is basically f of 0. And the question is asking us to explain why f of 0 is negative. So an interval that can tell us what f of c can possibly be is definitely going to lead us to our answer. An important use case of the Lagrange Error Bound is to construct an interval like so. And if you're wondering, this just simply stands for the Lagrange Error Bound. I just had to abbreviate. This over here is basically whatever the Taylor polynomial approximation was, which we found in part C to be -5. This interval tells us that f of 0 has to be negative even though we don't exactly know what f of 0 is. That's it for this video. Thank you for watching and good luck studying!